Computers. Most people believe that these systems are complex and perfect. In reality, although they are indeed complex, computers also have a sneaky flaw. This flaw has led to incidents that result in financial losses or, in some cases, fatal accidents. Computers are also part of our daily lives, helping us create moments, capture them, communicate, and, most notably, support our Netflix and chill moments. Anyways, to understand the issue of computer flaws, let's do this simple math equation on Google's calculator. If we type in this absurdly large number minus this other absurdly large number, the answer should be 1, but really the answer generated does not match the result we expect based on what we understand about math. We can also try the same calculation on calculator.net, a platform that has different kinds of calculators, and we get a completely different result. Even when we try a seemingly simple calculation such as 1.0 minus 0.9 minus 0.1 on calculator.net, the generated answer is once again incorrect. This calculation flaw that computers have has been costly in the past. In this video, we will be exploring why computers are bad at math. We'll also be talking about some of the accidents that have happened as a result of computer calculation errors. Computers come in several shapes, sizes, or forms, all designed to perform specific tasks individually or collectively as a system. So how does a computer do math? Here is my oversimplified and lazy explanation. We know that most modern-day computers are powered using electricity thanks to a couple of smart people who came up with a solution to use the flow of electricity to represent the binary numbering system in computers. They figured the easiest way to convey information in a wire is to consider it on or off based on how much electricity is going through it. An on wire represents 1 and an off wire represents 0. This small piece of information is called a bit, and it's the smallest piece of information that computers can process. You can group together on and off wires to represent a binary number. This gets more complex with the addition of more concepts like logic gates, transistors, and so much more. Since computers use the binary number system to do all computations, including arithmetic calculations, the base 10 number system we're used to gets converted to a binary number system for computers to understand. Take, for example, when we do this simple math calculation, 2 plus 2. Computers see this instruction in a different way by converting it to binary, 1 0 plus 1 0. What about a calculation like this, 10 divided by 3? We know the answer is 3.33333 with recurring 3's. The computer, on the other hand, which is limited by the number of bits it has no way of representing this number in binary. To account for this limitation, some more smart people came up with a solution that allowed computers to still calculate these numbers within a certain limit. Some of these solutions are the single precision floating point format or the double precision floating point format, which are still used today in most 32 and 64-bit systems. Here's a story. On February 25, 1991, during the Gulf War, an American Patriot missile battery in Dhahran, Saudi Arabia, failed to intercept an incoming Iraqi Scud missile, which led to the death of 28 soldiers. A report of the incident, titled Patriot Missile Defense, Software Problem Led to System Failure at Dhahran, Saudi Arabia, reported that the cause of the failure was because the missile defense system mistracked the incoming Scud projectile and instead scanned an area of airspace more than 500 meters from the missile. Without getting into the boring mathematical details, the error happened because the Patriot had been running for so long that the computer system, which was a 24-bit system, ran out of available bits to accurately calculate and monitor the area of defense. Consequently, performing the conversion after the Patriot had been running continuously for extended periods caused the range gate to shift away from the center of the target, making it less likely that the target, in this case a Scud, would be successfully intercepted. A nearly similar accident also happened on Tuesday, June 4, 1996. When the first flight of the crewless Ariane 5 rocket, carrying with it 4 very expensive scientific satellites, ended in an unholy ball of flames after 39 seconds. The explosion resulted in a huge financial loss and cost the European Space Agency approximately $370 million. The incident happened because a software process from the previous Ariane 4 rockets was used for the faster Ariane 5 rockets, and it captured an unexpectedly high reading for the sideways velocity of the newer, faster vehicle, but couldn't handle such a high figure. A self-destruct sequence was initiated and, a couple seconds later, later, the rocket was history. R.I.P. that rocket. Hey. Anyways, in history, there are many more incidents that have happened because of this simple-looking math problem that computers find hard to compute with accurate precision. But the year 2038 is one that might have some implicating effect in the near future, according to a programmer named William Porquet. Porkit. Many of you may remember the Y2K problem, in which there was a scare leading up to year 2000 due to potential computer errors related to the storage and formatting of data. Not long after that event, William Porkit had the idea of thinking ahead to yet another crucial date, Tuesday, January 19th, 2038. This is the moment when the number of seconds since January 1st, 1970 will exceed the maximum value that 32-bit systems can save date and time. In the first month of the year 2038, many computers may encounter a date-related bug in their operating system and/or in the applications they run. This can result in inaccurate dates being reported by the operating system and/or application. Why is January 19th, 2038 a special day, one might wonder? This is because Unix and Unix-like operating systems that power many important systems do not calculate time in the Gregorian calendar. They simply count time in milliseconds since their arbitrary birthday, Thursday, January 1st, 1970. Since it is a common practice in the computing industry to use a 32-bit variable to represent this number, the largest possible value for this integer is 2,147,483,647 and 2,147,483,647 seconds after the Unix time birthday corresponds to 3:14 a.m. Tuesday, January 19th, 2038. An additional second to that date and time will lead many Unix systems to revert their birth date in a manner similar to an odometer rolling over its limit in order to compensate for a value larger than that it can represent. Luckily, a couple of smarter people have come up with solutions and patched up systems that could be affected by this problem using a method called arbitrary precision arithmetic, also called big num arithmetic, multiple precision arithmetic, or sometimes infinite precision arithmetic. This method indicates that calculations are performed on numbers whose digits of precision are limited only by the available memory of the host system. This contrasts with the faster, fixed precision arithmetic found in most systems, which typically offers between 8 and 64 bits of precision. But quoting Porky on a blog he originally made as a joke, 2038.org, a large number of machines, platforms, and applications could be affected by the 2038 problem. Most of these will, hopefully, get decommissioned before the critical date. However, it is possible that some machines going into service now, or really old legacy systems that have never been upgraded due to budget constraints, may still be operating in 2038. These may include process control computers, space probe computers, embedded systems in traffic light controllers, navigation systems, etc. It may not be possible to upgrade many of these systems. And one last story. Sometime in April 2015, the Federal Aviation Administration, F.A.A., issued a warning about Boeing's 787 Dreamliner, saying that a software glitch in the jet's systems could suddenly shut off all electrical power to the plane mid-flight, causing pilots to lose control. This means that the control unit managing the delivery of power to the plane's engines will automatically shut down the engines if they've been left on for over 248 days. Hypothetically, this also means the engines could suddenly halt, even in mid-flight. So far, there is little to no information as to why this happened, but other observers have discovered that 248 days in centiseconds is 2,142,720,000. And the maximum positive value that can be assigned to a 32-bit signed integer is 2,147,483,647. By day 249, the number of centiseconds exceeds the maximum positive value, leading to failure. Fortunately, a temporary solution to this problem was to periodically shut down power systems while Boeing worked on a permanent fix. Hopefully, by Tuesday, January 19th, 2038, if some 32-bit systems are not patched, the age-old trick of turning it off and back on will help fix the problem. If you like this video, don't forget to hit the like button, and if you're not a subscriber, hit that subscribe button with the notification bell to get notified anytime a new video comes out.